Uh, it's a great pleasure for me to be here at this beautiful place. This is actually my first time here, although I've been to Bangalore many times. And also I'd like to thank the organizers for giving me the opportunity to speak here. And I also need to start with an apology. I haven't really worked on this particular topic of the conference, really thermalization or many-body localization, for some years now. And my talk is not really going to be related to that. It's about ground state phase of a particular model of quantum spin ice, where possibly if one was to study dynamics, maybe ideas of many-body localization might be relevant. So my talk is going to be about local entanglement and confinement transitions in random quantum spin ice models. And it's based on some work we've been doing with a student, Aniruddha Menon at UC Davis, and Tom Pardini and Stefan Aurige at Livermore. So the outline for the talk is as follows. I'd like to begin with a general introduction to quantum spin liquids and spin ice. I assume that not everybody is familiar with that. And then talk about the specific model that we'll study, which is Ising model on a pyrochlore lattice in random transverse field. And basically, as I mentioned, the talk is really going to be about ground state phases and properties of this model. And I'll briefly talk about the relevance of this model to rare earth pyrochlore magnets, and then end with summary and future directions. So there's been a great deal of interest over the past, I'd say at least 2 decades in looking for quantum spin liquid phases of matter. These are highly entangled phases, and I'll briefly discuss what I mean by that. They represent new paradigms of emergence in quantum matter, and that's why there's been such a great deal of interest in them. So a number of material systems are being explored, yet convincing demonstration of a quantum spin liquid phase is still missing. And one of the reasons, of course, is quenched impurities. So we are going to study a particular model of potential quantum spin liquid with quenched impurities here. So what is a quantum spin liquid? Well, the name really is drawn in analogy with the ordinary phases of matter that are based on motion of atoms and arrangement of atoms that we are all familiar with, namely solids, liquids, and gases. But here we are interested purely in the spin degrees of freedom. So imagine that you have a periodic solid which is fixed. Atoms are all fixed in their positions with unpaired spins. So we have magnetic moments, and they are interacting with some exchange interactions, and we already had models like that discussed earlier. So basically, spin liquid is about fluidity of spin orientation. Okay. So in analogy with solids, liquids, and gases, one would say that, so basically enthalpy typically favors periodic arrangement of spins, and so at low temperature, spins solidify in a crystalline or some kind of a solid or superstructure, basically forming ferromagnet, antiferromagnet, or some other structure. At high temperature, basically it's a paramagnet. Each spin essentially fluctuates independently. And the question is there when should one have an intermediate phase, which is a spin liquid phase, which has well-defined short-range order and yet continues to fluctuate, and if that can be pushed all the way down to 0 temperature, we'll call that a quantum spin liquid. So we know that as far as atomic motion is concerned and arrangement, the only system that forms a quantum liquid under ordinary conditions under at 1 atmosphere is basically helium, and it does so primarily because it is inert, so it doesn't favor a particular periodic arrangement really. I mean, any tendency to form a periodic solid is very weak, and it is the lightest of the inert gases, which makes it have large quantum fluctuations. So in the spin problem, basically this inertness is related to geometric frustration, because frustration, for example, if we have a triangle of spins interacting by antiferromagnetic interaction, so each one wants to be anti-parallel aligned basically, then on a triangle, out of the 8 possibilities for a spin half system, basically 6 of them are ground state. And indeed, as you go to a lattice of spins, if we connect these triangles into either a triangular lattice or into a Kagome lattice, which is a corner sharing lattice. Essentially, there's a finite entropy even in the ground state. That is, the number of ground states of these systems are exponentially large in the number of sites. So that geometric frustration is like inertness, and plus lightness basically translates into low spin. So when we have that, there's a possibility that you can have a quantum spin liquid phase. Sorry. So in terms of, on top of this highly degenerate subspace, when we add quantum fluctuations, so for example, if we have an Ising-like model on these lattices, which has an infinite number of classical ground states, if we add some quantum terms, such as transverse field term or transverse exchange terms, then generically two things can happen. A new ground state, that basically the finite entropy would be released and one would go to a ground state of the system, quantum mechanical system, and generically two things can happen. The new ground state could be a linear superposition of the many degenerate configuration, and this highly resonating entangled state of matter will basically be a quantum spin liquid. Or one could have a selection of a specific configuration as the global ground state. So this phenomena is generically known as order by disorder. Fluctuations of various kinds, including quantum fluctuations, can lead to a selection of a particular state within this degenerate manifold. So what we are interested, of course, is primarily in the quantum spin liquid phase. So quantum spin liquids must have global entanglement. So this idea first proposed by Phil Anderson in 1973 and then discussed by many other people. What we want really is the entanglement should not be just between a fixed set of spins, like forming singlets between these spins and these spins. If one only has a fixed set of, if the entanglement is only between pairs of spins, that would not be called a quantum spin liquid really. What one wants is a large superposition of such entangled states. And once one has this kind of global entanglement, then one really has the emergence of new degrees of freedom. Okay, that's basically what one is interested in. Typically, when one has a highly resonating state, then this leads to fractionalization, that is deconfinement of spin-on degrees of freedom. So for example, if you break one of these singlets, the two spin-on, these guys will be called spin-ons, and they can separate away and essentially become independent degrees of freedom. So when we are looking for quantum spin liquids, basically the search for quantum spin liquids is really a search for new degrees of freedom, new fractionalized degrees of freedom, and emergent gauge fields. Okay, so, and as I said, this is not yet established in real materials. So there are several candidate materials. There are the triangle. Yes, good question. Okay. So maybe we'll see some example later on, but let me first say this here. So fractionalization essentially within theoretical models is basically saying that your microscopic degrees of freedom, such as the electron, let's say, fractionalizes into two pieces. Okay, one could be a fermion with a spin, and the other could be a boson with no spin. Okay, holon and spin-on. But the system still remembers the fact in some sense that your microscopic degree of freedom is actually made up of these electrons. So these new degrees of freedom, they always have to satisfy some kind of a constraint. And that constraint essentially results in a gauge theory. Okay, so the expectation is that whenever we have this kind of fractionalization going on, there will also be emergent gauge fields. There are some exactly soluble models where this clearly happens. Okay, so there are lots of different material candidates for realizing quantum spin liquid. For example, there are a lot of triangular lattice-based materials going back to some organics which were studied more than a decade ago. There are Kagome materials, Herbert Smithites, that have garnered a lot of attention. There are a new class of materials called Kitaev materials, and there are also these rare earth pyrochlores which are known as the spin ice materials. And I'm going to focus here on the spin ice materials, basically Okay, so the challenge in establishing a true quantum spin liquid is as follows. Basically, first, there's no direct measurement of entanglement. Entanglement is very difficult to measure in a solid state system. There have been measurements of entanglement in cold atoms with tens of atoms, but this is probably not scalable because entanglement is inherently a many body measurement really. So what one would ideally like is to study properties of these fractional or emergent degrees of freedom, but they do not directly couple to external probes. Okay, as we understand these systems, an external probe like a photon or a neutron always couples to the bare microscopic degrees of freedom. So that means that these things can only be seen essentially as a continuum in scattering. So if we look at this picture here from paper by review by Leon Balens, basically if we have an ordered state and if we flip a spin, if a neutron flips a spin, basically that spin will have a well-defined energy momentum relation inside the solid. It will basically be a magnon, and one can see this in neutron scattering. This is how we look at magnetic systems in general. But if we have a system where there is fractionalization going on, then a flipped spin turns into two spin-ons, and as a result, one doesn't have a well-defined energy momentum relation. For any given momentum, there'll be a range of energies where the states can happen. So basically, one is indirectly looking for, so this remains one of the most important probes, but this is clearly an indirect probe. Okay, similarly, there are other kinds of probes. For example, if you have a gapless spin liquid, one could have power laws in heat capacity, susceptibility, thermal conductivity. So the main problem really, the main challenge in establishing a true quantum spin liquid is that disorder can mask or mimic many of these signatures. Okay, so how can you tell whether this is really coming from a true fractionalization? So in this talk, I'm going to focus on the role of disorder in a specific context of spin ice systems, which actually was proposed to maybe enhance the spin liquid behavior, where disorder was proposed as a mechanism for getting to a quantum spin liquid. So, any questions so far? So that was my general introduction to quantum spin liquids. Now I'm going to talk about the specific system, the spin ice systems. So the ice, basically as a solid, is molecular crystal of water, H2O. And if you ignore the protons, basically the oxygens form a four-fold coordinated lattice. And then there are twice as many protons, which means that on every bond between a pair of oxygen atoms, there's a proton. And the ice rules simply say that near each oxygen atom, there will be two protons close by, and two of them will be far away. Okay. Linus Pauling, long ago in the 1950s, actually realized that the system has a residual entropy. There's an exponentially large number of degenerate configuration where you can move the protons from one configuration to another and still maintain the ice rules. Okay, and then in the 60s, it was realized by Phil Anderson that actually if you have a lattice of corner-sharing tetrahedra, this pyrochlore lattice over here, and if you have strong anisotropy so that the spins, let's imagine that there are two preferred states of the spins which either point towards the center of this tetrahedron or towards the center of the other tetrahedron. And then if there are interactions between the spins such that two of them, I mean, if one points out, the other one wants to point in, then the best they can do for the tetrahedron of spins will be that two must point in and two must point out. And these configurations have exact analogy to the ice configuration. So this system was called spin ice. And it was not until 1999 that experimental systems were realized where, for example, Art Ramirez and collaborators measured the heat capacity of this particular system, dysprosium titanium oxide, where this dysprosium is an effective two-level system basically with this kind of anisotropy. And if you measure the heat capacity and then you integrate that, you find that the difference in the entropy between high temperatures and zero temperature is precisely the residual entropy that was predicted by Linus Pauling. So this is an example of a classical spin liquid where at low temperature one has a large number of degenerate configuration. The system also is famous because one can see that flipping a spin creates this dipole, the two tetrahedra become are no longer in the ground state, basically, and these two can be separated far away and essentially act as independent monopole degrees of freedom. The system basically is described by a vector field, a classical gauge field, basically a vector field with a zero divergence condition, and lots of properties have been studied, and these are actually fairly well understood. So the main interest over the last decade or so has been what happens when we have, when quantum... There's no SU2 symmetry here. So generally, that was one of the earliest definitions of spin liquids, was one that doesn't have a local order parameter. Now, it's possible that you can have spin liquid phases. The main thing about spin liquids is the entanglement. But it's possible that you can have spin liquid phases coexisting with some kind of a magnetic order as well. Okay. No, even long range is possible. So you can have a highly entangled phase which coexists together with, but that's not something that I'm going to be discussing here. Okay, but it is possible. People have discussed such states as well. Well, that's a good question. So I'm not being precise here. So the context in which one has a precise definition of a precise characterization of a spin liquid is really in gapped spin liquids, where there's a topological entanglement entropy, which is not related to any kind of boundary. Yes, but generically, large entanglement is going to be associated with quantum spin liquids. And yeah. This one. So this corresponds to R log 2 minus 1/2 log 3/2, and the upper one corresponds to R log 2. So the claim is that in zero field, if you take this measurement over here and integrate, you find that it goes to this particular value. The difference between low temperature and high temperature entropy is this much. So really what one should be doing is moving this high temperature entropy should be log 2. Okay, if it's a two-level system, well-defined two-level system. And so at low temperature, there'll be a residual entropy given by R times 1/2 log 3/2. That makes sense? So you should... That's the Pauling. So I will actually give you a derivation of that. Yeah, that's the Pauling value. Pauling had argued that this spin ice system, if you like, should have a residual entropy of R times 1/2 log 3/2. It's a mean field, but it's very accurate. And I'm going to give you a slightly beyond mean field as to why that is so accurate. Okay, so when we add quantum fluctuations to this spin ice of the right kind, in particular, it was argued by Hermeli, Fisher, and Balance that if you look at the XXZ model with a weak X and Y coupling equal but weak compared to the Z coupling, then that model should lead to a ground state which is highly resonating and essentially a quantum spin liquid. So the idea is that if you do perturbation theory, then before sixth order, the spin ice states remain degenerate, but in sixth order, the degeneracy is lifted basically by this resonance over here. The pyrochlore lattice has many of these hexagons of tetrahedra, and if you imagine that in a hexagon you have an ice configuration in which on this hexagon the spins alternate, one in, one out in every one of these tetrahedra, then In sixth order, you can tunnel from this configuration into this configuration where all 6 of them are basically reversed. Okay, and this tunneling effectively, when one does simulations, for example, leads to a highly resonating state in which now one has really a quantum U1, really an emergent quantum spin liquid where one has both fluctuating gauge fields, fluctuating magnetic and electric fields, and even in the absence of any charges, if you like, one can have propagating photons. And there's very nice work, for example, by Nick Shannon and collaborators telling us how neutron scattering in principle is supposed to see these things. Okay, but hasn't happened yet. So one thing very interesting about the pyrochlore lattice rare earth pyrochlore systems is that one has lots of possibilities. I mean, essentially, one can make these systems with almost all of these rare earth, all of these lanthanides. And in particular, they come really, one can divide them into two categories really, the Kramers and the non-Kramers. The half-integer spin systems, the degeneracy, of course, is enforced basically by the time reversal symmetry. But in integer spin systems, one doesn't need to have a twofold degeneracy. Generically, one would have non-degenerate states for single atoms, single ions, but one can have a twofold degeneracy coming from a symmetry like a lattice symmetry, and then any disorder will tend to lift that. So here's the paper that basically has motivated our work. It's by Savary and Bellens, disorder-induced entanglement in spin ice pyrochlores. So they were looking at, so they were basically arguing that if you have a non-Kramer system, then in general disorder will be like adding a random transverse field. And when you add random transverse field, so in particular, if we didn't have these field terms, this leads to all these degenerate spin ice configuration. And adding this random transverse field term, they argued, should lead to a phase diagram that looks like this. So this is, if you like, the mean value of the field, and this is the uncertainty, or let's say the standard deviation in the field. Then essentially, at high fields, one would get a paramagnetic phase. At low field, one should get this U1 quantum spin liquid phase, and then they argued that in this intermediate situation, one could have a Griffiths Coulomb quantum spin liquid phase. They also argue that actually MBL may be relevant to this model if one went to very high disorder, but we are actually not focusing on that here. It's in PhysRev letter, I'm sorry, yeah. I can send you later on maybe. About, I would say, 2 years ago. Okay, so first let's focus on the non-random system. The non-random system one can study basically by perturbation theory in H and 1 over H. And this was done by, again, Leon and Kai Schmidt and their student basically. And that's fairly, the expansion in 1 over H is very simple because at large H, essentially things are going to be polarized along the field direction, and then one can basically, it's a trivial ground state and it's easy to do perturbation theory in powers of 1 over H. On this, coming from this side, essentially, as I mentioned earlier, the model maps onto this ring exchange quantum spin liquid model. And there's a weak first order transition in this case. Okay, so what we are interested in is in studying the random transverse field Ising Hamiltonian. And we are going to study this again by exact diagonalization of systems with periodic boundary condition, by numerical link cluster method, as well as by perturbation theory. And the quantities that we are going to study basically are average moment along the field. So in the paramagnetic phase, there should be a polarization along the field, and it should become very small in the quantum spin liquid phase. Entanglement, the measure that we are going to use in this study is basically the entanglement of a single tetrahedron of spins with respect to rest of the system. So if you imagine just considering one tetrahedron, how entangled are the degrees of freedom in one tetrahedron with respect to the rest of the system? And we'll also study this Ising spin glass correlation sum, because actually we are expecting a long-range Ising ordered phase, long-range spin glass ordered phase in this model. So basically, numerical link cluster method is essentially a method that has the accuracy of series expansions whenever they are convergent, but they can be easily extended to random systems and include non-perturbative local effects as well. So the method basically works as follows. So whatever property one is interested in, if we choose an appropriate extensive property, it can be expressed as a sum over all clusters, a count called the lattice constant of the cluster, which is just a count of how many ways can that cluster be embedded in the lattice per lattice site, and a property called the weight of the cluster, which is entirely defined by calculating the property of the finite cluster and its subclusters. Okay, so this method can be used for generating series expansions as well, but it has the advantage that when one has, for example, a convergent high temperature expansion, then this will give us convergent results. When at high fields you have convergent high field expansion, this will also give us correct result. But it also builds in the short distance physics quite well. And it's ideal for spin ice systems when we use tetrahedral clusters. So for example, here's a calculation of the entropy, this Pauling calculation. If we look at the calculation of the entropy at 0 temperature and use this, so first one has a single site. Single site has an entropy of log 2. It gives us a weight of log 2, and per site count is just 1. So the entropy per site is just log 2. At order 1, one has one tetrahedron. One tetrahedron has 6 states, so the entropy is log 6. And its weight, when you subtract out the subclusters, becomes log 6 over 16. Its count is 1/2 actually per site. And so in first order, one gets exactly the Pauling answer. And actually, Jan Oitma and I had done this calculation all the way to 14 tetrahedra. And essentially, the answer is only changed by about 1 or 2%. So it's really an accurate calculation in this case. Anyway, so getting back to our model, when one does NLC for the non-random system, one gets a result that looks like this. This is the magnetization along the x-axis. And this is where one knows there's a phase transition, really. The NLC and the exact diagonalization studies, there's almost no difference. There's essentially very little finite size effect in this property in the paramagnetic phase. And here is what happens to the entanglement entropy. The entanglement entropy grows and it saturates to this value, which is essentially exactly log 6. So log 6 is also easy to understand. Basically, in the quantum spin ice phase, there are 6, if you like, each tetrahedron has 6 configurations which are all equally probable. And that's basically what one gets in this particular phase over here. So if you look at now, random exact diagonalization is very difficult to do for a finite system because already 32 sites means the Hilbert space is like 2 billion. So this is just showing the result for 16 sites. And what it shows is that if we fix some value of h, mean value of h, and vary the width w, then basically at some stage, what one finds is that the Ising correlations, they jump only a small amount in this finite system. And at the same time, the entanglement entropy dips. Okay, but this is a small system really that, and at the same time, almost nothing happens in this magnetization over here. So that comparison is telling us that basically this transition is happening essentially inside the spin ice subspace. Okay, so if one wants to do a numerical link cluster expansion, then the way to do this in this ice phase is to embed each cluster inside essentially a larger spin ice. Okay, so what time do I have left? 5 minutes. So I think I'm going to skip this over here and really just go to perturbation theory because that really will help us get the results for the thermodynamic system. So in order to really study this system and see what happens, what we need to do is really to first get an effective model from perturbation theory and then use exact diagonalization on that effective model. So basically, when we use perturbation theory for small h, basically, then this model reduces to a random ring exchange plus a random Ising coupling. So first of all, in fourth order perturbation theory, there's a coupling that there's an Ising coupling on each bond whose strength basically goes as hi square, hj square. And it comes, it's easy to see where that comes from. It comes from the fact that if we have one spin pointing out and one pointing into some tetrahedron, then if you imagine flipping this spin, then flipping this, then flipping them back, that's the fourth order process. The intermediate state when both spins are flipped, if one was in and the other was out, then this tetrahedron will remain in the ground state, whereas if both were in, then both will be pointing out and the other two were already pointing out, so one would have a highly excited state on this particular tetrahedron. So the intermediate states have different energy, and that leads to an effective Ising term on the bond, basically. And then in sixth order perturbation theory, one gets this ring exchange that we were discussing earlier. So essentially, one wants to do this model is actually, we can study up to n equals 64, but actually one could do even larger systems. Okay. So the phase diagram that we get looks something like this. So the perturbative regime, of course, is the small h, small w regime. And what one finds is that one transitions, it looks a little different from what was shown by Savary and Balens. Basically, one goes from quantum spin liquid phase into an Ising spin glass phase with long range order. And of course, if we consider these two as independent parameters, then for larger values of W or larger H and W, one gets into a Griffiths type phase, or what we are calling a random resonating hexagon phase, which is a variant of the random singlet phase. Okay, so let me just go to the results over here. Let me discuss what we get out of the numerical study. So first of all, if we look at the bandwidth, the energy difference between the lowest and the highest state, in perturbation theory, one can show that it will go as h to the power 6 in the uniform system. And then when W becomes large, as W grows, one would go into this intermediate stage where the Ising energies dominate. It should go as W square, H square. And of course, in this model, when one goes to very large W, it will go as W to the power 6. Okay, the entanglement entropy looks something like this. So one starts with this value of log 6. And then for small h, let's focus on these curves. These are for small h over here. There's very little size dependence, basically. This will go over to log 2 in the intermediate state over here. That corresponds to long-range Ising order. These are just cat states, two Ising ordered states. And then in this random resonating hexagon states, there's a little bit of size dependence, and one is getting some intermediate value. If we look at the Ising correlation sum, basically there's long-range order developing here, and one can see that this correlation sum is becoming proportional to the size of the system, and actually so does it over here. So this is a plot of what happens to this correlation sum. You can see that it is nearly saturated completely in this Ising spin glass phase. But the other phase, the random resonating hexagon phase, also has a percolating background with long range order. Okay, and actually one can look at the distribution of entanglement entropies. One has really, there's a sharp value at log 6 here. There's a sharp value near log 2 over here, but there's a broad distribution in this particular phase. Okay, so basically the phase diagram looks like this. There's a quantum spin. So if fields are weak, but there's a disorder, if the disorder is stronger than H, then essentially one is not going to be in a quantum spin liquid phase. Instead, one is going to be in this Ising spin glass phase. But this other phase is, of course, interesting. Well, I should mention here that there is also a nice paper by Chalker, Sherrington, and collaborators that says that in general, if you have a constrained subspace, and if you have weak random interactions in that constrained subspace, you can very easily get a spin glass order. The spin glass order is enhanced by having this frustration. Okay, we also looked at many-body inverse participation ratio, which again tells you that in this phase, basically there's essentially no fluctuation. These are just cat states here. You have obviously the quantum spin liquid, all states are essentially participating, but this phase also is interesting in that it also has an exponentially large number of states. But basically it can be thought of as resonating clusters which are with a background of spins which are Ising ordered. Okay, so let me just briefly mention that in the experimental systems, actually the only one that has been studied is this praseodymium zirconium oxide. The disorder is very large. So the W, if you like, is an order of magnitude larger even than J. And so such a system is not likely to have a quantum spin liquid. Of course, NLC, numerical link cluster, converges very well, was used by Owen Benton to show that you can get all the properties, basically thermodynamic properties. But it would be interesting if there were some evidence for these resonating hexagons in that particular system. That's something that we want to look for. How can one get a U1 quantum spin liquid in rare earth pyroclores? Well, if there's very low disorder and large mean value, then if there's very low disorder, one would need to have an H bar which is larger than W. Otherwise, it will clearly turn into a spin glass. One could have a very dilute site disorder because that actually does not create these Ising couplings, basically. One could also imagine, I mean, this is probably the most interesting case, is that one might have correlated disorder due to strain, which varies slowly over regions, and that could possibly still have a quantum spin liquid phase. And of course, if one has random direction but uniform magnitude in disorder, that could possibly lead to a quantum spin liquid phase. So it would of course be interesting to study dynamics in this model, and there are all kinds of interesting possibilities here. So let me leave my conclusion for people to read. Thank you.
Questions and comments?
Yes, I mean, it looks like it's first order from our numerical study. So I think already Balance and Savary were arguing for a first order transition, even when there wasn't a long range spin glass order. But this long range spin glass order should make it even more first order. So that's a kind of spin liquid, right?
Actually, also would that mean that there is actually also topological order in such quantum spin liquids?
Well, what do you mean by topological?
Well, I mean, several ground states
that together, I think.
Yeah,
so, yeah.
right.
So a class of quantum spin liquids that are best understood are gapped quantum spin liquids, and they have this topological entanglement entropy.
Right.
Okay, but this one is not a gapped spin liquid, and I don't know that there is a precise definition of entanglement.
Right. So as it stands, your definition is no local order and also no spin glass order, and yeah, that's it basically, right?
Well, my definition, it has to be a highly resonating state. My definition is that, or this is the definition that people will give you, is that the ground state should not be adiabatically connected to some kind of a cluster decoupled state, basically. Okay, so it should be some highly resonating state, which is the only way you can get emergent degrees of freedom.
Questions? Okay, so let's thank the speaker again.
Thank you.